So, we have at last come to the end of this 12-week long course on VLSI physical design. So, over the last 12 weeks we have seen lot of issues, lot of aspects on VLSI physical design and some of the challenges that are faced therein. So, here in this last lecture I will try to summarize whatever we have seen over the last 12 weeks. So, we summarize the total coverage of the course that you have seen so far. So, if you recall, during the first week we have looked at some of the basic concepts of design automation and how we can represent a design. Then we looked at the various design styles like standard cell, semi custom, full custom and so on, because we repeatedly mentioned there are many steps in VLSI physical design which are highly dependent on the design style that is actually being used. So, if we use standard cell design style for example, which is most predominant, some of the tasks become much simpler because your topology or the configuration or the structure of your circuits become much regular. Okay. And we also looked at the various steps that are required to be followed in physical automation. Now, during this second week we looked at some of the initial steps that are required for the VLSI physical design, like circuit partitioning was the first step we talked about. So, where a large design is divided into smaller pieces, then creating tentative floor plans for these partitions or blocks, then how to place these blocks, that means after the exact shapes and sizes and also the location of pins are fixed. So, how to place them. So, we looked at various algorithms in these regards and we also considered the specific design style related variations that can affect our decision as to which algorithm should be used. So, during third week we talked about the routing algorithms, specifically we talked about the grid routing problems. So, we talked about the algorithms like Lee's algorithms, Hadlock's algorithms, the various line search algorithms, and we also talked about the global routing problem. So, how we can represent it, the different kind of data structures and also some of the algorithms that are used. During the fourth week we looked at the detailed routing problem and the various solutions, in particular the channel routing algorithms were discussed, and then we started our discussion on the very important issue of clock design and the various timing issues that come therein. So, we continued our discussion in week 5 where we talked about how to design the clock networks, various clock routing architectures like H tree, X tree, method of means and medians, etc. And we looked at the various methods of clock tree design and the kind of hybrid approaches that are followed to minimize the clock skew, because we said this is very important. When you design a clock network, the main objective is to minimize the clock skew as much as possible up to the terminal points. And of course, we also looked at how to route the power supply connections, power and ground. Then we moved on to the timing related issues. So, in week 6 we started with some introduction to the timing closure problem. Then we looked at the very important issue of timing analysis, related problems of slack analysis and how to identify the critical paths. You recall the paths which have negative slacks, they are considered as critical paths in a design. False paths to remove unnecessary computations where possible, and lastly we looked at timing driven placement techniques, which are some refinement of the placement techniques we talked about earlier, where timing issues are also incorporated within the algorithms. Then we talked about the timing driven routing techniques, and this was followed by various physical synthesis techniques, where we can make some modifications to our netlists so as to meet some of the timing requirements or timing corrections that are required. So, we talked about gate sizing, introducing buffers, restructuring netlists, and finally we looked at a so called performance driven design flow. So, how this performance related issues or timing related issues can be incorporated during the various stages of the design, and then we looked at various approaches to timing optimizations. So, in week 8 we looked at some interconnect and layout related issues, like how do we model the interconnects. So, how do we estimate the delays of these interconnection lines. So, Elmore delay model, lumped RC models, various models we discussed there. So, we also talked about the design rule check and some design rules, lambda based design rules, and once these design rules are framed, so how a tool can automatically check whether these design rules are followed or they are violated. We talked about layout compaction techniques, which are again based on these design rules typically. So, these are some finer adjustments we do after the layout is completed. Before we do the so called tape out, we try to compact the layout, we try to do some visual inspection, try to see whether the design rules are satisfied. If there are some design rule violations, we try to correct them. These are the kind of methods or tools that we use to make one final look at the design and adjust the design if required, wherever some violations are detected. Okay. Now, during the next 2 weeks we looked at the another very important aspects of VLSI design, not only physical design, this is the aspect of testing. So, during week 9 we introduced the VLSI testing problem, particularly the digital circuit design and testing of digital circuits. We mentioned that how fault modeling is very important in this process. We mentioned how to reduce the number of faults using concepts like equivalence and dominance. Then we looked at some of the fault simulation algorithms, which are a very useful tool for the test engineers. We looked at some algorithms like parallel, deductive and concurrent. During week 10 we continued with our discussion on testing and looked at some basic concepts of test pattern generation. Then we looked at design for testability techniques, specifically the scan path method. We looked at one of the standards, the boundary scan standards, and finally built-in self-test technique, where we can design a circuit such that it can test itself. So, during week 11 we looked at some of the aspects of low power VLSI design, which is also very important in present day VLSI design. So, we looked at the basic concepts, various sources of power, dynamic power, static power, leakage power. We looked at some general techniques for power reduction. We looked at some gate level techniques also. At the level of gates, how we can make some changes so that power reduction is possible. And in this last week we looked at some architecture level techniques and also some algorithmic level techniques, where even at the higher level we have seen, if we can follow some techniques, it is possible to provide some significant saving in power dissipation when we finally synthesize our design into the layout level, up to the layout level. Okay. All right. Now, in addition, there will be some supplementary materials that has been provided. These supplementary materials actually provide some demonstration of the physical design automation process on some commercial CAD tools. So, here we have specifically looked at some of the commercial CAD tools like Cadence. We looked at some design flows with specific emphasis on physical design process, the back end design, and also special emphasis on static timing analysis and related issues. So, this exposure of the commercial CAD tools was not exactly meant to teach you how to use these CAD tools, but rather to give you an idea or a flavor of how these tools look like. But of course, if you want to learn or master these tools, you can use this introductory demonstration lectures to get started on it. You can go to a place where this kind of tools are available and have access to it and see how the designs and these tools are actually being used. So, once you use these tools hands on, only then you can have a real feel of the capability of the tool, because most of these tools are pretty comprehensive and huge. It is not possible to cover all aspects of this. Okay. So, these were the supplementary materials, and here I mentioned some of the main references. Like for VLSI design automation, we used references 1 and 2 and also the reference 4, and for testing mainly we used reference 3. But of course, you can understand nowadays there are so many other references available on the internet. You can have a look at the internet, you can see lot more materials available there. So, I should not, or I would not want to limit you by specifying only a limited set of references and saying that you do not look beyond this. I said that these are only for reference. There is much more comprehensive and up to date materials, and they are available on the internet, on the web. Please visit the web, search through the topics you want to understand and learn, and you will get much more deep insight into the topics once you go through them. The objective of this course was not to make you experts in these topics, just to make you aware of some of the challenges that exists. Okay? This is just the tip of the iceberg. If you are really interested, you need to study a lot more, go into the deep of these topics, possibly learn to use the CAD tools, because it is there where you are actually using these design automation in practice, and I believe in this way you can be a good engineer or an expert, so as to say, in these areas. Okay. So, with this we come to the end of this course, and I thank all of you for enrolling in this course, for attending this course, and I sincerely hope that this course has been of some help to you, either academically or professionally or otherwise, and we would really appreciate if you can provide some of your feedback regarding this course on the discussion forum that is available. That will be helpful for us really, so that we can possibly enhance or update some sections of this course on, or make some enhancements in future versions if we decide to run this course again in the future. Thank you very much once again.